This is the third and the last of the videos for Analytic Geometry Module 13. And in this one, we're going to look at the three problems that, or three of the many problems that Descartes solved. And here we go. Let's go to the document camera. So in this first one, I'm given two line segments. Come on, let's focus. One is my unit line segment. Its length is 1, and one has a line segment of A. And in this example, A is greater than 1. Okay, easy to see that. And what I'm going to do when I come down here, I've already opened up my compass so that it is set at length A. I'm going to put the point down here at the end of my line segment 1 and mark that point right there on the arc. Mark that point and draw that line segment. And let's label some points here. This is O, this is K, this is L. So the first thing I did was draw KL, line segment KL, so that the length KL equals A. Okay. So what we're going to do is what Descartes showed us how to do in his book, or in that appendix, La Geometry, is he showed us how to construct line segments that would have lengths of the higher powers of A. Now, this is really important because remember in geometric algebra, A was the length of a line segment, A squared was an area, A to the third was a volume. They didn't have any way to think about A to the fourth, A to the fifth, and so on. And what Descartes is saying is with my analytic geometry, these higher powers of any number can be represented by little old bitty line segments. No big deal. Okay, so once he did that, that was step one. Now he's going to come over here and he's going to draw a line, a second line segment, label that point M, that is parallel to that one that he just drew. Now, I'm not going to use a compass and a straight edge to do that. I'm just going to kind of eyeball it and see if that doesn't look parallel. It does to me. Close enough. All right, so that's capital M. This is capital N. Let's write down what we just did. Construct line segment MN so that KL and MN are parallel to each other. And then we're going to let X equal MN and the last thing we're going to do is find X. Okay. Now let's look at this. This looks a little bit like the picture that we had with our pseudo equality method with Fermat. I don't have right triangles, but I've got two triangles. One is embedded in the other. These two triangles, OKL and OMN, both share an angle. These two sides are parallel sides cut by a transversal. So these two angles are congruent. These two lines are parallel cut by that transversal. These two angles are congruent. These two triangles are similar to each other. So triangle OKL and triangle OMN are similar to each other. Now notice I was really careful when I wrote down those letters to make sure that O corresponds with O, K corresponds with M, and L corresponds with L. Got to make sure all that's lined up. They are similar to each other. Therefore, sides are proportional. Therefore, sides are proportional. So I know that KL is to OK as KLMN is to OM. Well, we know what the lengths of those four line segments are. KL is A, OK is 1, MN is X, OM is A. And when I solve that for X, I get X equals A squared. There you go. There's a line segment, one dimension, whose length is X squared. Now, what would you do to get X to the third? Well, I would take the length here. This X is equal to A squared. I would mark off A squared. Oh, too big. That's pretty close. I mark off A squared along here, A squared, and then draw in the line at this point that's parallel to this one. So I'm going to have going across the bottom of this angle, this side of the angle, line segments 1A, A squared, and so on. And then these parallel lines have length A squared, A to the third, and so on. Well, a question for you, you think about this, would be, what if A is less than 1? How would your drawing be different? How would your construction be different if A is less than 1? And think about it for a second. Suppose A is 1/2. Then when I square 1/2, I get 1/4. Cube 1/2, you get 1/8. Those line segments are getting smaller and smaller instead of longer and longer. So think about how you would do that one. All right, that's problem number 1. Here's problem number 2. Now, problem number 2 is to solve a quadratic equation. And he chose the quadratic equation that is set up with the quadratic term on the left-hand side and the other two terms on the right-hand side. AZ is the linear term. The constant he's representing as the square of a number. That's because he wants to draw two line segments. All right, what's the length of this coefficient of Z? My linear coefficient has length A. Draw that line segment. Take the square root of the constant and draw that line segment with that length. So from the given equation, I've got two line segments of length A and B. Okay, then what do? Well, then I draw a circle whose diameter is A. So the length across here ends the center of the circle. From O to N to P is that length A. A is that right there. And then I just drew a line from the center of the circle to some point. I drew the tangent line at that point. How would I do that? You know, I knew from Euclid's Elements that a radius and a tangent line at that point are perpendicular to each other. So if I've got a radius, I would just construct a line that's perpendicular to that one. That's how I got that tangent. Nothing calculus about it. It was pure Euclid. All right, so drew the radius, drew the tangent line. And then what we say it is tangent to line L, the line segment LM. So extend this line segment out to M, and that has length B. Okay. Now what I'm going to do is draw the line. This line gets drawn last. I'm going to draw the line from M through the center of the circle. Okay, draw that line, and it's going to intersect that circle in 2 points O and P. Okay, remember the order of my construction. Draw a circle whose diameter is A. Draw a radius, construct a perpendicular, lay out the length B along that line, and then just draw the line from M through the center of the circle and mark those points O and P. That's where O and P come from. Okay. So here's the deal. Descartes said, according to Descartes, OM is a solution of our equation. All right, remember the equation? The equation, you can't see it up here. Let me write it right here where you can see it. Z squared equals AZ plus B squared. In other words, OM equals Z. Well, what I want to do is figure out some kind of a way to express the length of that line segment right there. O to M is that long line segment right there. There's O to M. I want to figure out how to represent that length in terms of the coefficients of the equation that I started with. So I need to figure out a way to represent OM in terms of A and B. So the problem is to represent OM in terms of A and B. Just using what I did from my construction. And I'm going to have to do that on this other page and refer back to my picture every now and then. All right, well, first thing, notice this tangent line is perpendicular to the radius, which means that's a right angle right there, which means NLM is a right triangle. It's a right triangle means I can apply the Pythagorean theorem. So this side squared plus this side squared equals this side squared. All right, let me write that down. So I know that LN squared plus, there's LN, plus that length right there, LM squared, is equal to the hypotenuse squared, which was MN. Leg squared plus leg squared equals hypotenuse squared. All right, well, what are these things? LN is a radius of the circle. I know that the diameter of the circle is A. So what's the radius of the circle? It's half of that. So the radius of the circle would be A over 2. Okay. What's LM? LM. Well, when I drew LM, I figured out where M was going to go so that LM would be equal to B. So LM is B, so LM squared is B squared. All right. So I can take that equation and solve it for MN. I get A squared over 4. I'm going to combine these two fractions. A squared over 4 plus B squared equals A squared over 4 plus 4B squared over 4 equals A squared plus 4B squared over 4. And that's equal to MN squared. So MN is equal to the square root of that fraction, A squared plus 4B squared over 4, which is the square root of A squared plus 4B squared over 2. Okay. Well, I'm not quite there yet, but I've got MN in terms of A and B. Go back and look at your picture. What I want is OM. And what I have right now is NM. But wait a minute. OM is just ON plus that one. It's just these two line segments put together. So the length of OM is ON plus MN. And ON is another radius of the circle. So that's A over 2 plus the square root of A squared plus 4B squared all over 2. And if I combine those two fractions, I've got A plus the square root of 4B squared all over 2. That's what Z is. Z is A plus the square root of 4B squared all over 2. This sounds a little bit like a quadratic formula, doesn't it? Now, if you want to actually verify that that is a solution of that equation, substitute that expression back in over here for Z and do all the algebra and the arithmetic, and sure enough, you'll get the same expression on both sides of the equation. It does work. Okay. So if we've got the equation Z squared equals 5Z plus 6. Remember, the analytic geometry was this connection between geometry and algebra. And so what Descartes said was, I could draw this circle and that line segment is the one that's going to solve that equation. Well, we're just going to do the substitution. Let's just substitute these numbers in here. We get Z equals, this is A, and in this case, A is 5 and B squared is 6. So I've got 5 plus the square root of 4 times 6 all over 2. So 5 plus the square root of 24 over 2. And no, wait a minute. I forgot to add the A squared here. A plus, put A squared there, put A squared here, put plus 25 here, put plus 25 here. Wonder why that didn't turn out right. So I've got 5 plus the square root of 49 is 7. 5 plus 7 is 12 over 2 is 6. Sure enough, Z is 6. 36 plus 30 equals 30 plus 6. That works. Okay. And if we took this equation and we factored it, z squared minus, get everything on one side of the equation, minus 5z minus 6 equals 0. When I'd factor, I'd get z minus 6 times z plus 1. I'd get that equals 0. I'm going to get two solutions, z equals 6 and z equals -1. Well, Descartes only got one solution, but think about it for a second. He's using geometry to solve the algebra problem, so his solution is going to be the length of a line segment. There's no way he's going to get the negative solution using this method, because you'll not get -1 as the length of a line segment. Okay. And then in his law geometry, he's also got examples where he takes other forms of the equation and takes the same picture, but has other parts of that picture, other line segments are solutions to other equations. All right, now here's problem number 3. To construct the tangent to the parabola, y squared equals ax. Now notice this is not a function, or it wouldn't be if I drew the bottom half of it. Y squared equals ax. We're just looking at the top half of it at the point AA. Okay. Well, here's the plan. We're going to draw a circle centered at this point x10, and we're going to draw the line segment. It's centered here so that AA is on the circle, which means this will be a radius. And if that's a radius of the circle, to get a tangent line, all I have to do is draw a line segment that's perpendicular to that one. And the line segment that's tangent to the circle will also be tangent to the parabola. Okay, so all I have to do is figure out where to center my circle. I need to find the coordinates of x. Well, I need to find the value of x. Find the coordinates of that circle. Okay, so that's the game plan. The game plan is to find the coordinates of the center of the circle, then draw my radius, then construct the line that's perpendicular to that radius, and I'll get my tangent line. Okay, so here we go. First of all, the point, the center of the circle is going to be on, because of symmetry, the center of the circle is going to be on the x-axis. So the y coordinate of the point is 0, which means I really only have to find the x coordinate. That's good. So the equation of my circle remember, the general form of the equation of a circle is x minus h squared plus y minus k squared equals r squared. Just brackets. So I know what the center is for my circle. It's x10. So for my circle, hk is x10, x1 comma 0. So I've got the equation x minus x1 squared plus y minus 0 squared equals r squared. So x minus x1 squared plus y squared equals r squared. And by the way, once I know what x1 is, I'll be able to find r, because the radius is just going to be the distance between this point and the point AA. Okay, so since the point AA is on the circle, I can substitute AA in for XY and get a minus x1 squared plus a squared equals r squared. Okay, well, remember these two are equal to each other. Both of these are equal to r squared, so I'm going to set these two left-hand side expressions equal to each other. X minus x1 squared plus y squared equals a minus x1 squared plus a squared. All right, you remember what y squared was? Y squared is ax. Okay, that's what the function is that we're talking about. Y squared is ax, so I can make that substitution. So x minus x1 squared plus ax equals a minus x1 squared plus a squared. Let's multiply everything out. X1 squared minus 2x x1 plus x1 squared plus ax equals a squared minus 2ax1 plus x1 squared plus a squared. Well, a little bit simplifies. X1 squared, I can subtract from both sides of the equation. Let me move everything to one side of the equation. And I'm going to write, this shouldn't be x1 squared. This should be just x squared. Let me bring everything to one side of the equation. So I've got x squared minus 2x x1 plus ax. Bring this over plus 2ax1 minus, I've got two of these a squared, so minus 2a squared equals 0. Okay, now I'm going to group these two terms together and these two terms together because they've got common factors. So these two terms have x as a common factor. So let's factor out an x plus x times negative 2x1 plus a plus factor out 2a times x1 minus a, and that's equal to 0. Okay, now this is a quadratic equation. This quadratic equation has only one solution, because the circle and the function y squared equals ax meet at only one point. Okay, when we set those two equal to each other, we're looking at that particular point right there, where it can be represented on the circle and on the function. Set them equal to each other. Well, there's only one point where those two equal each other. Okay. All right. So which means the quadratic equation only has one solution, which means when a quadratic equation, this is tricky. How in the world did he think of this? When a quadratic equation has only one solution, it looks like x minus c squared, and I probably equals 0. And I probably shouldn't say it looks like. It can be represented in this form. It's got a double root if it's only got one solution. And that one solution is c squared. I'm sorry, that one solution is c. All right, so let's take a look at this. If I expand this, I get x squared minus 2xc plus c squared equals 0. Compare these two equations. They both have x squared. These two terms correspond with each other. These two terms correspond with each other. Okay, that's a constant. That's a constant. What have you got in there? You've got an a and an x1. X1's a number. Now, granted, we're trying to figure out what that is, but there's only one of them. There's one value for x1, so it's a constant. This right here is the linear term. There's x. There's its coefficient. There's the x. Its coefficient is negative 2c. All right, so let's set those equal to each other. Let's take x times negative 2 x1 plus a and set it equal to negative 2xc. Okay, that's those two terms. Set them equal to each other and see what we get. Well, we can divide both sides by x. I get negative 2x1 plus a equals negative 2c. All right, I'm going to stop right there for just a second. Oops, stop right there for just a second. Because over here, I want to do the same thing, but with the constant terms. Take 2a times x1 minus a. Set that equal to c squared. Okay. And let's see what we can do with that. All right, well, I'm going to actually just leave it alone for a minute. All right, now take a look at this. We've got two equations here. I'm trying to figure out what the value of x1 is. A is what's given. C's a variable. You know, two equations, two unknowns, x1 and c. I want to solve this for x1. That's what I'm trying to solve for. I'm trying to solve it for x1 in terms of a. Let me remind myself what I'm trying to do. I'm trying to solve for x1 in terms of a. And this is where I'm like, well, several places, but here I'm thinking, how did he know to do this? Take this first equation and let's square both sides. We're going to keep working down here. Square both sides. And I get negative 2x1 plus a squared equals negative 2c squared. On the right-hand side, that's 4c squared. And on the left-hand side, that's, I'm just going to leave it as negative 2x1 plus a squared, quantity squared. Just leave it like that for a second. Over here on this side of the equation, over here on this side, working with this equation, let's multiply both sides by 4. and I'll get 4 times 2a is 8a times x1 minus a equals 4c squared. Oh my gosh. This equals 4c squared. This equals 4c squared. That means that negative 2x1 plus a squared must equal 8a times x1 minus a. Now look, I've got an equation that just has x1 and a in it. If I can solve this equation for x1, I've done it. All right, well, let's multiply this left-hand side out. I get 4x1 squared minus 4x1a plus a squared equals 8ax1 minus 8a squared. Bring everything over to one side of the equation. You've got 4x1 squared. I'm going to subtract 8 of those, so that'll be minus 12x1a. Add that to both sides, plus 9a squared equals 0. Holy cow. This right here factors to 2x1 minus 3 times 2x1 minus 3. Set that equal to 0. It's a double root. So 2x1 minus 3, minus 3 equals 0, means 2x1 equals 3. x1 equals 3. I lost my a somewhere. Where did I? 2x1 minus 3a. Equals x1 equals 3a over 2. Oh my gosh. That's it. So if I go back over here, here's the deal. Here's my x-axis. Here's that graph of y squared equals ax. If I find 3a over 2, 0, here's a, here's 3a over 2. Here's the point AA. Draw in that radius of my circle. There's my circle. Draw in the tangent line at that point. There's my tangent line. Now, how would I find the slope of that tangent line? Well, I know this is the point 3a over 2, 0. I know this is the point AA. Descartes actually shows us later on how to find the slope between 2 points, and we know how to do that. It's the difference in the y coordinates over the difference in the x coordinates. It's going to be a minus 0 over a minus 3a over 2. I believe it's going to be negative 2a or negative 2. A minus 0 over a minus 3a over 2 is a over negative a over 2. Sure enough, that simplifies to negative 2. So the slope of that tangent line, I'm sorry, the slope of this line is negative 2, which means the slope of the tangent line is 1/2. And doesn't that look like it would be about right? If you were to draw in the tangent line right there, it's 1/2. Wow. That's pretty amazing. That's a lot of work. And it really does make you appreciate calculus. And what would we do? We would take this y squared equals ax. First of all, we write it as y equals the square root of ax so that we could take the derivative of it. And then set that derivative equal to 0 and take it from there. Okay. So that was Descartes' third problem, or the third problem from Descartes' work that we're going to look at. And all three of those, I hope, give you an idea of how he made the connection between algebra and geometry, and also how he is thinking about these pre-calculus ideas. He's thinking about the tangent lines and slopes of tangent lines to functions at particular points. Well, that's what we did all through Calculus 1. But he's thinking about it from a different point of view. He's using algebra and geometry instead of calculus. All right, so our next module is on probability. The next one is on number theory, and then we hit calculus. Oh, no, we don't. We've got one more in there on the parallel postulate, I believe. All right, so there's still a lot of math going on before we get to what's going on with calculus. All right, talk to you then. Bye-bye.